When a metal is placed in its aqueous solution, for example, I have shown you a crude example here. When it is placed in an aqueous solution, a potential difference develops and this is called an electrode potential. Now, when this solution is taken as 1 molar at 298 Kelvin, which is 25 degrees Celsius, then you call that electrode potential as standard electrode potential, represented by E naught. If the metal is negative compared to its aqueous solution, oxidation occurs. For example, M gives you Mx plus X electrons. So this is oxidation. So then the potential that you get is called oxidation potential, whereas if the metal is positive with respect to its solution, then reduction occurs. Let's say Mx plus X electron gives you M. So in that case, this is reduction potential. Oxidation potential is when something is getting oxidized, reduction potential is when something is getting reduced. You can use either of them for a given problem, but one thing that you have to be absolutely certain is, when the question says electrode potential or standard electrode potential and I don't tell you oxidation or reduction, then it absolutely means reduction. Even if the example is given this way, for example, this is printed for you, they don't tell you E naught OP, they say the standard potential is, then it means it is reduction. This is by IUPAC convention. So if they give you an oxidation equation and they have to tell you that E naught OP to make sure that they are giving you oxidation potential, otherwise it is assumed as reduction potential. So this is something that you really want to know. Now that I know, this is the most important one, reduction potential, unless oxidation potential is given. Now they are related in such a way that E naught reduction potential is exactly equal in magnitude but opposite in sign of the oxidation potential. So you can convert one to the other. Now you may have two different cells. Now how do you know which is going to get oxidized and which is going to get reduced? So I need to know the E naught values. Now to know a reduction potential, it is very hard to quantify a reduction potential unless it is a reference to an electrode. There are a couple of reference electrodes you can use, but the most common one and the one that comes for U and JEE mains and NEET is always going to be standard hydrogen electrode or SHE electrode. Sometimes it is also written as NHE electrode. JEE advanced might have calomel electrode or they can reference it to some other electrode, but for you guys it is always going to be compared to the potential of that of standard hydrogen electrode. The standard hydrogen electrode is a simple setup where you have H plus electron gives you H, and I'm going to get 2 here, so I can put a 2 here and I can put a 2 here. Or you can also write H plus 1 electron gives you half H2. So this equation or this reaction is what is given as reference for us, H plus going to H2. This is assigned a value of 0.00 volt and everything else is measured accordingly. So anything that is positive compared to this allows to get reduced, anything that is negative compared to this allows to get oxidized in preferential to this electrode. So that means if I give you two different electrodes, you can figure out which is going to be oxidation side of the reaction, which is going to be reduction side of the reaction by looking at their E naught values. But you have to compare the same E naught values. You have to compare E naught reduction potential with E naught reduction potential or oxidation versus oxidation. Now here is a list of E naught values, the electrochemical series. If you look at it, the concentration is always 1 molar and 298 Kelvin. You want to be sure about that.
I have selected only few that are important for you to understand a trend. Now what you want to know is there are two ways that a table can be given. You don't need the table for the exam, but you should be able to interpret a set of data. Hence it's good for you to look at the table. Two ways a table can be given. One is in terms of the strongest oxidizing agent on the top, or more specifically the most positive value going to the least positive or the most negative value. In that table, the fluorine is always on the top and lithium is always on the bottom. The other type of table that is printed is exact same, no difference, just inverted, meaning lithium is on the top, fluorine is on the bottom, the values are inverted. I like to use it this way, it's much easier. Now what you want to get from this table is all the species on the left side are getting reduced. And it's easy when you want to compare, all of them are written in terms of reduction. And the ones that are getting reduced are basically oxidizing agents because they oxidize others. So all these are oxidizing agent, and this number tells you their potential to get reduced, meaning their potential as an oxidizing agent. So the top left is always going to be a oxidizing agent, the strongest among them, and similarly the bottom right is going to have the strongest reducing agent among them. So in our table right here, fluorine is the strongest oxidizing agent. My lithium is the strongest reducing agent. Now many things can be arrived from this table. Let's look at this. Are halogens. So right here I have a halogen. Here I have a halogen. Bromine right here and iodine right here. If you see the halogens, we can say the reducing tendency in the order fluorine greater than, bromine greater than iodine. Fair enough, electronegativity. Also, if you see electron gain enthalpy is a different order. You would have seen in periodicity under me, electron gain enthalpy of this order. Now, in both cases, you're going to gain electrons, even here over there as well. But why does the change happens? Because this is in a gas phase, this is in an aqueous phase, 1 molar aqueous phase standard. In aqueous phase, fluorine overtakes chlorine because it has very high hydration energy. Hence this order. You want to remember the order of halogens. And also a couple of things we can say is in organic chemistry, if somebody asks you, what are the oxidizing agents you know, you're most specifically going to say these. And obviously they are higher up the table. Few things we can see here is, let's put a triangle as a symbol. Are metals, noble metals. Partially noble copper, coinage metals, right, more specifically. You see that they are in the order of reactivity this way, meaning our gold is greater than Ag greater than copper, and actually turns out that platinum will be higher. So this is something you want to remember, and also you want to remember right here is our reference. So all these are noble metals. They don't want to get oxidized, meaning they love to get reduced. They like to be in the zero state. I mean, particularly in this order. We will see later this equation is useful for us. It's actually very useful. We can use this to calculate the moles of electron for every molecule of oxygen. One molecule of oxygen is liberated from water. It is 4-electron process. This is going to come in Faraday's law. Now, you don't need to remember the entire table or the values. They'll give it to you. Remember a couple of orders, that is easier. Anything below hydrogen, it's going to have a negative value. But you can see here, you have your even nickel that is pretty stable. It's right below hydrogen. You have your everyday use iron is below that, and zinc is way below hydrogen. So zinc can be used to protect iron. If there is iron 2 plus formation, it will react with zinc to give you iron back. It's used in galvanization of ships. Now, if you see here, I have my aluminum group 13, way lower electropositive element, and also these are group 2 and group 1. You can see that lithium right here and sodium right here. So they love to get oxidized. They are very electropositive metals. So hence they are lower down the order. They actually love to get oxidized to the corresponding metal ions that they catch fire. For example, lithium catches fire, sodium actually catches and liberates so much of heat. As I said, you don't need to memorize this table. Just go through what I just said a couple of times, watch it over and over, and you will be able to appreciate electrochemistry and it will get a lot easier.
So I have chosen three different species and I have written them in the order where my top is going to be more positive, going to through 0 to more negative. Now if I were to match them up, so what we just learned is what you have on the left side is oxidizing agent, what you have on the right side is reducing agent. And the oxidizing agent strength as you go down the series decreases. So this is going to be the most oxidizing, meaning wants to get reduced. So this is going to be the weakest oxidizing agent. So the reducing agent strength increases as you go down the series. So this is going to be a reducing agent. This is the strongest reducing agent. This is the weakest reducing agent. When you have your electrochemical cell, your galvanic cell, the reaction is always, if you have multiple species in a given cell, the reaction is always going to be between the strongest oxidizing agent and strongest reducing agent to give you weakest oxidizing agent and weakest reducing agent. For example, let's look into our given set of example. My strongest oxidizing agent is copper 2 plus aqueous plus strongest reducing agent is zinc 0 solid gives you. Now weakest oxidizing agent is going to be zinc 2 plus aqueous. Weakest reducing agent is going to be copper 0 solid. Now basically what we have is Daniell cell. So what we have in Daniell cell is copper 2 plus getting reduced, zinc 0 getting oxidized. Now we can see here the reaction, if it is spontaneous, is always going to be oxidizing agent reacting with the reducing agent, and if there are multiple species present in there, then it's always going to be strong reacting with strong to give you weak reacting with weak. So we can calculate the E naught cell. E naught cell is E naught cathode minus E naught anode. Here cathode is the one that is getting reduced. My copper is getting reduced, so that is going to be cathode. Zinc is getting oxidized, that's going to be anode. So I have 0.34 minus, this is negative again, minus 0.76, that is 1.1 volt is the E naught of Daniell cell. You want to remember that value, and they usually give you the values of E naughts, but you want to remember these three at least. You want to remember that.
This is a NEET 2012 problem. Here they have given you the standard reduction potentials of 4 different half cells. Couple of things we want to see is all of them are given as reductions. That's good. And they are actually given sequentially. You see there it goes on decreasing. Now they are asking you what is the strongest oxidizing and reducing agents. First thing we want to do is make sure that they are given in proper sequence. Here all of them are given as reduction. That's good. It can be given as oxidation also, as long as all of them are oxidation. Reduction is better. So that's what we have, and it's also second thing you want to check is whether they are in a sequence. So 2.85 is greater than 1.36, which is greater than 1.06, which is greater than 0.53. So based on our knowledge of electrochemical series, we know that this left side is the oxidizing agents, and the strength of the oxidizing agents increases as you go up, or it decreases as you go down. So this is our strongest oxidizing agent, and this would be our weakest oxidizing agent. Similarly, reducing agent strength as you go down the series increases. So this is going to be our strongest reducing agent, and this is going to be our weakest reducing agents. Here they're asking you what is the strongest oxidizing agent, that is going to be our F2, and strongest reducing agent, that's going to be our I2. The option is A. As simple as that. This is asked in NEET 2011. The standard electrode potential of three metals are given X, Y, and Z, and they're asking you to arrange them in reducing power of these metals. Reducing power, right away, that means they want to get oxidized, meaning they're asking you to arrange them in the order of their reducing power, meaning they're asking them in order of reducing agents. Reducing agents love to get oxidized. Now, the standard electrode potential they have given you, as I taught you, when they say electrode potential and they don't specify, then it means standard reduction potential. You cannot take it as oxidation. So now what we have is X, Y, and Z. So we can write it as X, Y, and Z, or maybe on the left side, doesn't matter. Maybe they might go, because they said metals, I put it on the right side so that they have reduced from some metal ion to metal. So the values are minus 1.2, 0.5, minus 3.0. So if you were to arrange them in the order, you see that zero point 0.5 is greater than minus 1.2 greater than minus 3.0. That tells me Y greater than X greater than Z. This is in terms of standard reduction potential. Standard reduction potential tells you the order of the species trying to get reduced, meaning oxidizing agent. Here they are asking you reducing power, so it will just be the opposite. Y, X, Z. So that will be the reducing agent. So Z greater than X greater than Y. That will be our option, Charlie. This question was also asked in NEET 2011. A solution contains, you have a solution, you have Fe2 plus, Fe3 plus and I minus. These are present together. This solution was treated with iodine I2. It was treated with I2. E0 for the two species are given here. This converting into these two, this converting into these two. These numbers are given. Both of them are positive. Okay. The favorable redox reaction would be, now when you look at the E0s, this is reduction. This is also reduction. So this is more positive. So this is going to go here and this is going to get oxidized. Both of them cannot get reduced. So Fe3 plus will react with I minus. So the reaction is going to be the strongest reducing agent and strongest oxidizing agents react with each other to give you the corresponding species. 2I. So there's going to be two of them here just for electron balancing. Now what can we say? I2 will be reduced to I minus. That is wrong. I minus will be oxidized to I2. There will be no redox reaction. That is also wrong. There is going to be a redox reaction. I minus will be oxidized to I2. Fe2 plus will be oxidized to Fe3 plus. No, Fe3 plus gets reduced to Fe2 plus. So there is only one correct answer, Charlie. Let's look into a NEET 2006 previous year question. An hypothetical electrochemical cell is shown below. So we know from our practice, reactant anode gives you product anode double bar, reactant cathode gives you product cathode, and a reactant gives you corresponding product, reactant gives you corresponding product. So this is going to give you this is going to give you this. Okay, that's the way they have given you. Okay. The EMF measured is plus 0.2, meaning this is going to be a galvanic cell. So this is going to be spontaneous. If this is spontaneous, then Ra reacts with Rc. So A will react with B plus to give you A plus and B. So right there, simple. So this question became extremely simple because I stuck with my notation. I wrote it so it's easy to reference. Just don't keep staring at this and try to do it. Instead, write this down. It makes it easy for you.
We can calculate the EMF of a given cell by doing E0 cathode minus E0 anode. So when I say E0 cathode and E0 anode, as I told you, IUPAC definition says it's always going to be reduction potential. So we can expand this and write it is going to be E0 cathode reduction potential minus E0 anode reduction potential. So now we can play with this. We can convert this as E0 cathode reduction potential plus E0 anode oxidation potential. So this and this are going to be exactly same since the reduction potential is same in magnitude, opposite in sign of that of oxidation potential. Now what we can do is we can convert this if you want. This can be E0 cathode oxidation potential becomes a negative sign plus E0 anode oxidation potential, or we can write it as E0 cathode oxidation potential minus E0 anode reduction potential. These are the different ways in which you can write. Now, you can take a negative sign outside. E0 cathode oxidation potential plus E0 anode reduction potential. Now, if you see these two are exactly opposite. Negative sign is here, reduction potential, oxidation potential, reduction potential. These two are exactly opposite. Reduction potential positive, oxidation potential negative, reduction potential negative, reduction potential negative. Now, one year NEET question has come where they just gave you 4 different options and they asked you which one is going to be correct. So you can do any of them, it doesn't really matter. This is the absolute must that you have to know. Do not try to memorize these. If the question comes, you can always convert one from the other. The other pattern that comes in NEET, it has come many times, how to calculate E naught of a given cell from two different reactions. Now you want to be very careful. For Daniel cell, for example, you have copper 2 plus 2 electron gives you copper 0, positive 0.34, zinc 2 plus 2 electron gives you zinc 0, solid minus 0.71. So if I were to do it, this is my cathode, this is my anode. So I can do E naught cathode minus E naught anode equals 1.1 volt. This is extremely simple. But there are cases, and it has come many times in NEET. We have our copper 2 plus 2 electron gives you copper 0, and copper plus 1 electron giving you copper 0, copper 2 plus 1 electron giving you copper plus. Again, states are aqueous, correspondingly aqueous, and zeros are solid. Now if you look at just the notation, this reaction as it is, I can leave it. If I flip this equation and add, I should get this copper 0 cancels out. Okay. Now that's what I have done here. If I flip this equation, I get my final. Now flipping is not the correct way of doing electrochemistry. You don't want to flip because reduction becomes oxidation. It is better to do one minus the other, but for convenience, we just want to score points, so we can just flip the equation. If I keep 1 and subtract it by 2 or flip second equation, I should get this. Now this is how a typical question would look like. They have given you the values as well. I picked up the values from the standard table. Now this pattern has come many times in JEE and NEET, and most of the time it is copper example over and over. They may give you out of the 3 any 2D equation and ask you the third one. So if you were to do this, if you subtract it straight away, okay, you will get a negative value, and also you will have a different number, but that's not the actual answer. So how you want to do it is, we can convert the E naught to delta G's, okay, for both of them, and then convert this back to E naught. Now, if I convert this to delta G and convert it to delta G, then I can get the delta G of this equation and I can convert it to E naught. How do you get the delta G for a given reaction? It's given as delta G naught equals minus NF E naught. Okay, I'll combine this with thermodynamics soon. So, this is how we do. So, if I were to do this, delta G naught 3 equals delta G naught of first equation minus delta G naught of second equation. So what we can do, minus NF E naught 3, so it is N3 equals minus N1, F E naught 1 minus of minus plus N2 F E naught 2. I can cancel my F. So what I have is E naught 3 equals, I'm going to take care of my symbol, the negative goes to the other side, N1 E naught 1 minus N2 E naught 2 divided by N3. Okay. This is the way you want to do. So when do you choose this method? When I can directly do it, when do you choose this method? There is actually a fundamental key here. If you look at this equation, the final equation, copper 2 plus zinc 0 gives you copper 0 plus zinc 2 plus. The final equation, there are no electrons present. Whereas in the final equation, I have electrons present. So if the target equation they are asking you has electron, they don't have to give you the equation, they can give it to you this way. What is the potential for Cu2 plus Cu0? Cu plus. See, there is one electron process. So obviously, it has electrons in it. So it is going to have this setup. So now, this is good if you do E naught 1 in reduction potential as well as E naught 2 in reduction potential. Some people do this in reduction potential, this in oxidation potential, the sign changes, however you want to do it. If you want, make a note, both E naught 1 and E naught 2 are reduction potentials, hence you get a reduction potential for this one. Okay, this is how you do, and this has come many times. Okay, now what I have done is I am just making it clear in the board. So E naught 3, we just got this formula. So N1 is 2 electrons, so N1 is 2, E01 is reduction potential 0.34 minus N2 is 1 electron times the corresponding 0.52. I didn't flip the equation, so I'm using a negative sign, divided by N3, copper 2 plus going to copper plus 1 electron process, then you can do it. This is how you do this particular problem. Now this has come in terms of common examples that you will see are iron 3 plus 2 plus 0, copper 2 plus 1 0, tin 4 plus 2 plus 0. So what it means is there are 3 different oxidation states. You can go for anything that has more than 2 oxidation state. So how many reactions are possible? This can go to this, this can go to this, this can go to this. 3 reactions possible. Same here. Out of the 3 they will give you 2, they will ask you 1. So this is the way you want to do. Determine whichever one is your E0, whichever one is your E0 1 and E0 2, correspondingly E0 3 can be calculated. Similarly, for example, tin can go here, tin can go here and 2 plus can go. If I were you, I would be happy if I get this question because this pattern is not printed in NCERT, but it has come in NEET many times.
Let's look into a NEET 2011 question. The standard reduction potential for tin couple is given and that for chromium couple is given. So right from here we can make sure that this is reduction, this is also reduction. So they're talking about same type of reaction. That also tells me that tin 4 plus loves to get reduced more than chromium getting reduced because of the values. This is positive, this is negative. These two couples in the standard state are connected to make a cell. So obviously this is going to be our cathode, this is going to be our anode. Reduction is going to happen, oxidation is going to happen. E0 cell is E0 cathode minus E0 anode. That's going to be 0.15 volt minus of minus plus 0.74. So we have 0.89 volts. Simple. Now, when I connect these two, what you get is, maybe I can write this down, tin 4 plus chromium gives you tin 2 plus chromium 3 plus. Tin has gotten reduced, chromium has gotten oxidized. Whatever electron the tin wants is given by chromium. So this is a full reaction, one half cell reacting with another half cell. Because I'm reacting half cell and half cell to give a full cell, I don't have to go through the delta G formula, straightforward. Here is a good example that came in NEET 2011. This is very similar to the one I just solved for you guys on the board today. The electrode potential for the given two cell reactions are given. Both of them are positive, good, and both of them are reduction, good. The E0 value for this reaction would be. A couple of things that you want to see is right away, if you see here, this plus 2 electrons. So this is a half cell. If it is a half cell, you have to go through the formula that we just saw. E03 equals N1 E01 minus N2 E02 divided by N3. Now you can take whichever one as N1 and N2 depending on how you're going to see it. So final reaction, I want Ce2 plus on the left side. So this is my first equation, this is my second equation. Alright, so now if I add the equation as it is, do you get this? Ce2 plus and Cu gives you Cu plus is here. If I add it, I will get Cu2 plus giving you Cu. So I'm basically going to add the equation, so I don't have to use this. I can just put a plus sign here. So this sign depends on whether you are adding these two equations or you have to flip one of them. Again, flipping is not the right way, doing a minus is the right way. So this is not a formula that is set in stone. This symbol alone will keep changing depending on how the reaction is given. So if I add these two, everything cancels out to give you Cu2 plus 2 electrons gives you this. So our E03 would be N1 is 1 electron here, N2 is 1 electron. They combine to give you 2 electrons, so N3 is 2 electrons. So 1 times 0.15 plus 1 times 0.5 divided by 2. That's going to be 0.65 by 2, 0.325 volts. So again, make sure you know your target equation is a half cell or a full cell, and accordingly do this way or straight up reaction like Daniel said. There is a similar pattern that has been asked in NEET 2006. Two different half cells are given and they're asking you what is the EMF of this particular cell. Now, what do you see in this cell? No electrons. There is no electrons. Whatever this gives, this takes. So this is a full cell. Two half cells combined to give you full cell. I don't have to go through the complicated route. Straight away I can do. Now what I need to do is I need to have Fe on the left side. Here, this is the reduction potential. Fe2 plus 2 electron gives you Fe441 minus. But I want Fe on the left side, meaning basically let's call this equation 1. I have to flip it. This is Fe3 plus on the left side. I have Fe3 plus on the left side. So this is equation 2. So basically I have to do 2 minus 1. If I do 2 minus 1, what I have is 0.771 minus of minus 0.441. So we have 1.212 volts. Now here, if you look at the electron count, this is 2 electron, this is 1 electron. So I have to multiply this equation by 2. If I multiply this equation, does not mean this will get multiplied, because E naught does not get multiplied like your delta H or delta G. E naught is a intrinsic property. You don't multiply based on the amount you take. There's a NEET 2001 question that we can solve. Standard electrode potentials for Fe2 plus Fe, half cell is given, another half cell is given. So they're telling you three different things, species are kept. So there is one species here which is same here, this here, this here. Okay. Now there is two ways to do it. One is you can guess right looking at it, or you can write the reactions. I would say for a beginner, write the reaction is much easier. Let's write the reaction based on the values, more positive right here. So this is going to be the one that I'm going to write first. Fe3 plus electron gives you Fe2 plus, this reaction. Then I have minus 0.44 volts, Fe2 plus 2 electron. If these two I keep, obviously you can see that the SOA will react with the SRA. So these two will react. So what happens right now is my Fe3 plus will decrease. This is wrong. Fe3 plus will decrease. Fe2 plus will increase and Fe0 will decrease. So I have Fe3 plus decreasing, Fe decreasing to give you Fe2 plus higher. So now what we have here is this is increasing, not true. This is decreasing, that is true. The ratio of these two remains unchanged, impossible. This is decreasing, this is increasing. How can the ratio be unchanged? So this is also wrong. Fe2 plus decreases, no, it increases. So that is your option. This question was asked in NEET 2009. As I told you, copper example is extremely important. The same things they keep asking you. You guys can practice it yourself. It's similar to the one that we solved in class. So look here the pattern. There is three equations for copper. They can give you any two, ask you the third one. Right away I see plus electron. So this has to go through E03 equals N1 E01, N2 E02 divided by N3. Now is it positive or negative depending on do you have to flip any equation. Now when you see this, I'm not going to add these two equations because that won't give me this. If I want this equation, I have to make this oxidizing, right? I have to flip this, copper plus goes to the other side, that way copper 2 plus. So that means this is going to be N1 E01 minus N2 E02 divided by N3. Accordingly, you can calculate. I'll leave the calculation up to you guys. You can practice it yourself. This is the important thing about Echem. It's hard to understand once you are learning it, but once you get it, you can actually score extremely well.